Hey Royals, in this lesson we're going to look at a concept that you may remember from grade 11 physics, and it's this idea of work. Now, you may remember that work deals with a force and a displacement, and both force and displacement are indeed vectors. So you may remember this equation from previous physics courses, and now that we've worked a little bit more with vectors, you understand that vectors, when they're multiplied together, there's a option of either a dot product or a cross product. This is something that you might encounter in calculus class. But for now, what we're going to do is we're just going to say that the dot product of two vectors can be represented based on the magnitude of the two multiplied by the cosine of the angle between their tails. Okay, so that's what we have right here. It says the angle is always measured between the two tails of the vectors. Okay, so I have an example down here to see how does the actual angle affect the result when we're multiplying two vectors together. Okay, so in this case here, I have vector A and vector B with an angle between their tails of 0. So they're both pointing in the same direction, which would mean that the cosine of the vector, or the cosine in between them, would be the cosine of 0 degrees. Now I've put a parent function of a cosine on the right hand side of our page here, and you can see that at 0 degrees the value is 1 for cos. So that means that when we were to put it into the equation, f is f times d, and this should have a little vector above it, cosine the angle, that would mean that it just simply comes out to the magnitude of the two vectors. Right, so we get that work is a maximum. Okay, so work's a maximum if we have the angle between the vectors as 0. Now let's increase the angle a little bit. Let's say that it's something less than 90, but it is larger than 0. Now if we look at our cosine function, something that's larger than 90, less than 90, but larger than 0 would result in cosine values that are always going to be positive. So say we take 45 degrees, and 45 is around here. You would get a positive value. If you take something closer to 90, you still get a positive value, and we're talking about the y-axis, right? So that means that the cosine, and this one was equal to 1, the cosine of the angle will be larger than 0, which results in the dot product being larger than 0, because the magnitude of a vector can't be negative. So, let's go back to that. So that means that we will get that work is greater than 0 in this case. Right? Now, what happens if we get straight at that 90 degrees? So if we're right at the 90 degrees, the value of our cosine function is, in fact, 0 on the y-axis. So that means that cosine of 90 is equal to 0, which means that the dot product will result with an answer of 0. So work is equal to 0 if we have that the vectors are 90 degrees to each other. Okay, now let's go a little bit larger than 90 degrees, but less than 180. So we can see that in this region between 90 and 180, you do get negative values for our cosine function. So you can see that these all now result in negative values on my y-axis, which means that the cosine of the angle is going to be less than 0. So that results in the fact that our dot product will get a result that's less than 0, which means that our work in this case is less than 0. All right, now just like 0 was an important point for us when the vectors were pointing in the exact same direction, let's look at what happens if we have our vectors working in opposite directions. So say the force is going left and the displacement is going right. So obviously they are 180 degrees to each other. You can see that on our cosine function graph, you get a result of -1. So if the cosine between the angles is, say, 180 degrees, you get an answer of -1. So that means that the dot product will come out to just the magnitudes of the vectors, but they will be a negative maximum. So it is a work is a negative maximum. Okay, so we can see that the angle actually comes into play quite a bit when we're talking about work, right? So the magnitudes of the vectors won't change. It's just simply the cosine between the two tails will indicate if we have positive work or negative work. So knowing which direction the vectors are pointing is going to be very important in this case. Now, one thing I want to point out to us is that even though we're working with vectors and we're multiplying vectors, the result that we get for work is always a scalar quantity. So you shouldn't have to worry about directions with work. And the other thing that we're going to mention is the units on work. Okay, so I'm just going to come up to our equation here, and I'm going to say, all right, let's deal with the units of work here. So let's say the units of work is going to be the units of force, so that was Newton, multiplied by the units of distance or displacement, which is meters, and then units of cosine, well, that angles don't have units. You can say degrees, but we can drop the degrees for our discussion here. So the units for work actually comes out to be a Newton meter, right? So the units that we're dealing with here are Newton meters. However, you may remember this as another unit called the joule, right? So Newton meters or joules, both of which are acceptable results when we're talking about work. Okay, so let's take a case here and go back to discussing our vectors. So one thing that we can always think about is if we're doing positive work, we're actually increasing the energy of the object. Now imagine this, you have a box, you're pushing it in, say you're pushing east and the box is moving east. Well, the box is going to accelerate, or the box is going to start moving, which means that you're actually giving energy to the system, or you're giving energy to the box. Now, if work is negative, you're actually removing energy from the box. So say you take the same box that you're pushing and you stop applying a force on it. That means that friction's going to come into play. Friction's acting to oppose the motion, so it's going to slow the object down, and it's actually removing energy from the system. So you can say negative work is actually the same as removing energy from the object. Okay, so let's go through an example here on looking at the different amounts of work done on a object. In this case, this object is a cart moving through a displacement of 10 meters. So we're going to assume that the displacement is in this direction, and that's going to be, let's say 10 meters, like it says in the question. Okay, and let's go through each of the individual forces to find out what the amount of work done on this cart is by that force. Okay, so let's determine the work done by the applied force. Now the applied force is acting at an angle of 30 degrees above the horizontal, and it has a magnitude of 112 newtons. So then the displacement is along the horizontal direction. So the angle between the force vector and the displacement vector is going to be 30 degrees. Okay, so let's work out the work. So work is equal to the magnitude of the force vector, and we'll call it the applied force vector, and then it's the magnitude of the displacement, cosine, the angle between them, so we'll say cosine of theta. Here we have the applied force, the magnitude of it is 120 newtons. The displacement is 10 meters. And then the cosine of between the tails is 30 degrees. Now, if you punch that through your calculator, you get an answer of 969.95 joules, or for our argument here, we'll call it 970 joules, right? Or Newton meters, if you would rather that. Okay, so we can see that the applied force is actually adding energy to the system, or to the cart. Let's determine what the gravitational force is doing. Now, if we look at our picture here, gravitational force is acting straight downwards, and the displacement is acting towards the right, which means in this case, the angle between these two vectors is 90 degrees, right? So we can say here, I'll just write over to the side, theta is 90 degrees. Okay, so that's important to us. So if we start working into our equation, work is equal to the magnitude of the force, and we'll say the magnitude of the force, that's gravitational, multiplied by the displacement, cosine, the angle. We could go ahead and calculate the force due to gravity. We don't really know the mass of the cart, so I'm just going to write the magnitude of Fg again. The displacement is 10 meters. But the important part here is the cosine of 90 degrees. And we know that the cosine of 90 degrees is in fact equal to 0, which means that the work done by the gravitational force is 0 joules. Okay, so the gravity force does no work on our system because the angle between these two vectors is 90 degrees. Let's go down and talk about the normal force then. So we've talked about the applied force, we've talked about the gravitational force. Let's talk about the normal force, this one up here. Again, if we think about the box, it's moving towards the right. The normal force is acting upwards on our page right now. So the angle, again, theta, is going to be 90 degrees. Now, same argument that we made before. We could go through it really quickly. Work is equal to the normal force times displacement vector, cosine the angle, and the normal force, again, we could calculate it if we knew the mass of the object. We have 10 meters as a displacement, and then the cosine is still going to be 90 degrees. Same result that we found with the gravitational. You get that the work done is 0 joules. So because there's no displacement in the vertical direction, there's no work done in that direction. Cool. So let's talk about the work done by the frictional force then. Now, if we think about the frictional force, displacement is towards the right, the frictional force is towards the left, which means that the angle that we're dealing with is 180 degrees. I'm just going to put up here theta is equal to 0 degrees, just so that we're consistent with our angles being labeled. So let's work through our equation. Work is equal to the magnitude of the frictional force multiplied by the displacement multiplied by the angle between their tails. So the frictional force we were told in the question was 52 newtons. So I'm just going to put down 52 newtons. Displacement, 10 meters. The cosine of 180 degrees. And if we work through that on our calculator, we get that it's negative 520 joules. I'm just going to change my negative sign. There it is. Negative 520 joules. Cool. So we found out that because this work is negative, that means that friction is actually removing energy from our cart. So we can actually calculate the overall work done on the cart. So for this, we're going to think about the horizontal direction and the vertical direction as slightly different things. So we can figure out the work done in the horizontal direction, and we can figure out the work done in the vertical direction. So work in our sense, the total work being done could be thought of as the work in the horizontal and the work in the vertical. But we're just going to talk about the total work being done. The only displacement that's happening is in the horizontal direction. So I'm only going to worry about the work in the horizontal direction because that's the only result that we actually have. So it would be the work done by the applied. Now I've added A, N, G, and F to my work equations just so I can think of what work or where did this work come from. So this is the work done by the applied force plus the work done by the frictional force, because those are the only results that we found in the horizontal direction. So if I put in my values, I get 970 joules plus negative 520 joules, and you get a result of 450 joules. So that indicates to me that the work done on the cart is 450 joules, which means that I'm adding energy to the cart. which makes sense because we're causing the cart to move. We're gaining energy with that cart. Another way of looking at the same situation would be to look at the net force acting on the box or on the cart or whatever object we're dealing with. So if we were to look at this system here, we know that there is no acceleration up or down. There is no net movement in the vertical direction because this cart is just simply traveling across a horizontal floor, which means that the net force that we're dealing with is only in the horizontal direction. So I'm going to say that my F net X is going to be the result of my two vectors. So my two vectors in the horizontal direction are FA plus FF. And I'm actually going to add in some directions here. FA plus FF. My FA was 112 newtons. Cosine of 30 degrees, because that's the horizontal component of my applied force, and that's acting towards the right, plus 52 newtons, and that's acting towards the left. Let's make sure our vectors are pointed in the same direction. So I get cosine of 30 acting towards the right, minus 52 newtons acting towards the right, which gives me an overall net force of 44.99 newtons acting towards the right. Okay, so if I were to now take that, there's my net force. I can calculate the work done on the system just simply by saying, okay, work is equal to the magnitude of the net force multiplied by the displacement, cosine the angle between these two. Now, if we think about the net force, it's only acting towards the right. So my angle here, theta, is actually 0 degrees because I'm only dealing with the net force and it's going in the direction of my displacement. If we remember, our displacement was towards the right. Okay, now let's substitute in our values. We get 44.999. There's two nines and then a 5. If you actually went through with your calculator, that's my net force. My displacement was 10 meters. The cosine was 0 degrees. And we know that cos of 0 is 1. So this just simply becomes 44.995 times 10. So you get 449.95 newtons, which rounds to Newton meters, which rounds to 450 joules. So you can see that you get the same result as before, even though we dealt with just looking at the net forces. All right, interesting. All right, so both of these examples, or in this example, we dealt with a force that was constant. The force didn't change at all. It just simply was 112 newtons towards, on an angle of 30 degrees towards the right. And there was a frictional force that was constant at 52 newtons. What if there was a force, or our forces were not the same all the way through? If they changed? Well, in this situation, we have two different approaches that we can take. I can graph the force versus displacement, and on the right-hand side here, we have that exact example. You can see that the force increased over a period of the first little bit in the motion, and then it was constant throughout. So maybe I'm trying to get an object started, I'm pushing on it, getting over that static friction, and then kinetic friction comes in, and we have the object sliding at a uniform velocity. So how can I figure out the work that's going on here? Well, if you remember from before, a lot of information can be pulled out of these types of graphs. So the area under that curve, so if I think about the area under that curve, it would be force times displacement if I was calculating the area, right? And it's a triangle, so I would have 1/2 the force times the displacement. But again, force times displacement, that's work. So I can say that the total work done on this situation would be the work done for, let's call it area 1, plus, if this has now a rectangular area, it would be plus the work done for area 2, right? So you can calculate those just based off of the areas. So that's kind of neat. What if I didn't have a graph? What if I just had a situation that I was lifting a 10 kilogram mass up into the air by 1 meter? So thinking about this situation, what would happen is initially you would have to have a force greater than gravity to get this box moving. So that would be a acceleration. But once I get it moving, I lift it at a constant speed through the air, and then I come to a stop. While I'm moving it at a constant speed through the air, we have that the force of gravity is equal to the applied force. So the applied force is equal in magnitude to the gravity force. Now, if I was going to bring it to a stop, in this case, the gravity force has to be a little bit larger than the applied force to cause acceleration downwards, which would slow the box down and eventually come to a stop. So on average, in this situation, the force required is equal and opposite to the force of gravity, because we think about the starting and the speeding up and slowing down as essentially canceling them out, and you get this average in the middle of a constant motion. So during that motion, so I'll draw my box here, you have the applied force acting upwards, and you have your gravitational force acting downwards. Okay? So let's look at the work done by this applied force. Okay, so we said that the work is equal to the magnitude of the force, magnitude of the displacement, multiplied by the cosine of the angle between their tails. So the work done by the applied force, and we said that the applied force is equal to the gravitational force in magnitude. So the work done by the applied force is the force of gravity. The displacement we said was, well, in this case, let's say just displacement, d. And then the angle would be 0 degrees between the direction of motion. So this was our displacement. It's acting upwards. So the angle between the applied force and the displacement vector is 0 degrees. Okay, substituting our values, mass is 10 kilograms. Local gravitational field intensity is 9.8 newtons per kilogram. You get a displacement of 1 meter. The cosine is 0 degrees. And you get 98 joules for the work done by the applied force. Okay, so let's think about, all right, gravity then. How much work does gravity do on our muscles? Well, in this situation, the gravity is pulling downwards. The displacement is acting upwards, which means the angle between these two vectors is 180 degrees. So the calculation is the exact same, except that the angle goes from 0 degrees to 180 degrees. And that results in us getting an answer of negative 98 joules, which complements the idea of conservation of energy, because the energy that I put into the box is removed from me in the form of work being done by gravity, right? So this is a conservation of energy, because the energy that the mass gets is what I lose, which is kind of cool. All right, so that concludes our lesson here on the introduction to work. I will also put up a worksheet for us to work on with these same kind of concepts.